Thank you, Kevin. So welcome everybody to our third webinar for 2021. This is the third in our mini webinar series. Today we are trying out a new format to maybe improve and widen our reach to a larger number of people and to different target groups. We do this by interacting, by inviting guest speakers with partners, with companies we work together with, maybe in European funded projects. And that is the example we have today. We are looking at the MASSTART project that we are involved in together with several other partners, but specifically today, I am joined by Bogdan Sirbu from the Fraunhofer IZM and Paraskevas Bakopoulos from NVIDIA. We will move through the usual steps in the introductory phase of this webinar. Kevin, next slide, please. As always, we have the giveaway. So the items we have for 2021 are not illustrated in this picture on the slide, but we have some new items special for 2021 because this is our 20th anniversary year that ficonTEC has been in the business of photonics assembly and test. I have two questions today because I think the first one is too easy. So I've made it a double whammy question. Answers into the chat, please. And the first person to get both questions right will be the winner of our giveaway lucky bag for this webinar. When was the internet officially born? If you can give me an exact date for that, that would be useful. And the second question is, so today we're talking about optimizing throughput and tools for maximizing number of channels and the efficiency of putting data through the internet, through the fiber backbone. We're talking about hardware, but what is the crucial software tool or aspect that is responsible for reducing internet traffic and arguably making it even possible in the first place? Answers into the chat, please. January the 1st, 1983, Maureen, well done. You have got the first question again. Very well done. Let's see if the second one comes up. So, ficonTEC news, very briefly, because we have a lot to cover today. ficonTEC is hiring. If anybody is interested or anybody knows somebody who might be interested, check out our careers page or pass on the link. Thank you very much. Laser World of Photonics China opens today. We can only sit here in the Western world in envy and look on as China, for example, and in some other parts of the world, get to enjoy real events with real people and real interactions. ficonTEC is represented there. I'm sure maybe some others here from around the table as well. It'll be interesting to see how that result pans out on what the level of interest and attendance is. Very important webinar dates coming up on April the 7th, wafer level tester development. So for the last 2 years, we've been working intensively on how to optimize and drastically reduce or drastically improve wafer level testing capability. And we've started releasing some products to initial customers, and we want to present some of those results and what our ideas and plans are in a webinar on April the 7th. Should be a very interesting topic. That will be together with Torsten Warenkamp, CEO, one of our most frequent partners, actually, for the webinars. Next slide, please, Kevin. So at this point, I want to move on to the main topic, which is the MASSTART. I am not the person that knows the most about this project. This is the other three people who are joining me today. Carla, ladies first, Bogdan and Paraskevas. We are going to start with project coordinator Fraunhofer IZM with a short presentation from Bogdan. Bogdan, please, the stage is yours.
Thank you, great. Hello, everyone. So, yeah, my name is Bogdan Sirbu, and I will be introducing a little bit the activities we're doing at Fraunhofer IZM, and in particular the project MASSTART. Yes, next, please. Next slide, please. So a few facts about Fraunhofer IZM. So we are basically offering advanced packaging solutions for integrated electronics and photonics. We are one of the 74 Fraunhofer institutes all over the world. We have more than 8,000 square meters clean room and lab space in 3 locations in Germany, Berlin, Dresden, and Toulouse. We are more than 430 employees with a turnover of more than 35 million euros, and more than 40% of this is direct industrial cooperation. And, we are founded somewhere in 26 years ago. Next slide, please. So traditionally, we've been focusing on microelectronics, micro integration, and our R&D research should be placed somewhere between TRL 2 and 7, and most of the applications we've been focusing on are medical engineering, industrial electronics, ICT, automotive, and semiconductors. And when it comes to the photonics, next slide, please. Yes. And when it comes to photonics, we are focusing on the same type of TRL, so basic research bringing to production, so TRL covering 2 to level 7, and most of the applications are focused on communication, sensing, and lighting. So we're working on bringing photonic systems on panel level and wafer level.
Bogdan, if I can interrupt you with a question, maybe for the viewers, can you perhaps give us a little bit of detail about how you intersect with the other divisions within the IZM? Are you drawing on all of the microelectronics experience you have in the past and applying what you can to photonics?
Yes, that's correct. So traditionally, we've been focusing on integration of microelectronics, and a few years back, we've tried to bring photonics into that with sensing and integrated peaks within the systems. Okay,
thank you. Please carry on.
Yeah. Kevin, please, next slide. Yes, and when it comes to the photonics value chain, so we are a one-stop shop. So we are doing the system design, we're doing our own peak design in terms of photonics, RF, free space optics, mechanics. Despite the fact that we are back-end, traditionally we are like back-end focusing on the clean room, we're processing our own peaks based on silicon nitride and polymer platforms, but most of the activities, the photonics-related activities at the institute are in the integration and packaging concepts, so 3D integrations, micro-optical benches, RF integration, and so on. And we finished the value chain with the characterization, which is done also in-house.
Are you, sorry, if I can, another question. So on this slide, we see silicon-based, we also see indium phosphide and polymer material systems as part of the smart integration approach. Do you work with all the material systems, or do you have ones that you specifically focus on?
It's our platform is based on silicon nitride and polymer based, but we have collaborations with other partners providing indium phosphide chips or electronics, and we are doing the entire packaging and integration concepts in-house.
Okay, good to know. Thank you.
Now, Kevin. Yes, and we've been focusing in the last years on the photonic interconnects for data centers and next generation computing, and one of the first projects addressing this topic was the flagship project Foxtrot, and there we developed 480 gigabits per second transceiver with 12 channels receive and transmitter based on a 3D integration concept on silicon interposer. And we saw back then the potential of the co-packaging technology, and we participated in the matrix project, developing the 1.6 tera switching matrix with 64 channels receive and transmitter, where the entire optical coupling was done with a 2D fiber array. And we ended up with the MASSTART project where we develop a 1.6 terabits per second, 16 channel WDM transmitter. Next slide, please.
Oh, if I have another question. So co-packaging. So this is obviously something that IZM has been involved with before. MASSTART is not dealing strictly with co-packaging, correct?
That's correct.
Was that a decision that was made at the start simply because of the time frame involved, or?
We developed this concept based on the requirements from the product owners. So these concepts are developed by Das Photonics and Melanos, now NVIDIA, and they saw a huge potential in this type of transceivers for future products.
Okay. Paraskevas, if I can ask you, what sort of time frame do you see then the advent of co-packaging? At which point is co-packaging going to become important for NVIDIA? And do you see the ability to transport what you're learning within MASSTART into that aspect as well?
So that's a very good question, and thanks for bringing this up. So co-packaging is actually a sort of a buzzword lately. Everyone is talking about co-packaging, and you can see it in every roadmap, in everyone's roadmap. We believe, and I will also discuss about it in the next slides. So we believe that in the longer run, we will need to go to co-packaging. We will definitely need to go to this type of form factors, but there is still some time and some generations where pluggable optics will continue to be relevant until we have to switch to the co-packaging. So that actually brings us some time to come up with mature solutions. We might see some intermediate, some in-between solutions until we get there to co-packaging. But of course, we are taking this into account in MASSTART. We are ensuring that all these assembly processes and automation processes are applicable also to a future, let's say, deployment in a co-packaged optical engine.
Okay, thank you. So as you should be doing, you're working together, right? So very good. Bogdan, thank you. Please continue.
Thank you. Yeah, and on this slide, I just wanted to show that in order to enable mass manufacturing of data photonics projects, you have to rely on automated manufacturing with high throughput of assembled pieces per minute and so on. The transceivers have to have high data rates, higher than 1 terabit per second, and of course you have to be cost competitive. And for that, you have to have some proven design based on PDKs and develop your own chips and take care of the integration and packaging, as well as testing and ending up with the standardization. So the main message here is that we have to improve the cross-fertilization between photonics and other technologies in order to enable mass manufacturing of photonics for data.
Okay.
Next slide, please. So in MASSTART, within the consortium, we have several companies. We have some technology providers. Letting is putting their silicon photonics platform. Fraunhofer IZM is bringing the TSP technology. In photonics provides their coupling technology based on glass waveguides called WAP. And Alma, for example, is bringing the indium phosphide chips. We have within the consortium design house in charge of the entire layouting and PDK generation and so on. We have ficonTEC doing the photonic assembly, and in terms of testing, Tektronix and the University of Thessaloniki are in charge here. And of course, the system providers, so the WTM-based transceivers are owned by Photonics and NVIDIA, and the current transceivers by ADVA. Next slide, please. And on this slide, some of the highlights of the project, the main building blocks, basically the Leti silicon platform. We have the ALMA chips, lasers developed within the project. We have the coupling schemes from Team Photonics for edge coupling or grating coupler based coupling schemes on the PIC. We have the silicon bench from Photonics involving isolators and such components to relax the coupling, the alignment tolerances. And of course, we're relying on their expertise for assembly and testing from ficonTEC and electronics. And in terms of integration concepts, we're counting on the expertise of NVIDIA. And with this, my part ends. I'll hand it back to you, Craig.
Well, not quite. Hopefully, you're going to join us for the rest of the discussion. But I have a question. So at what stage are you with the demonstrators are all coming from Just Photonics? Is that correct? And what stage are you with those? Or maybe not, maybe somebody's shaking their head. I'm open to the correct answer.
So we are working on it. So basically Just Photonics is doing the assembly on the silicon bench, and that will be assembled on the PCB by NVIDIA. So we are currently finalizing the PIC fabrication, and the next in the following months we will go into the assembly.
Okay. Good. Thank you, Bogdan. Thank you very much. I see no questions in the chat at the moment. Just a reminder to all our viewers, please, if anybody has any intermediate questions, you can just add those to the chat and we will try and answer them live in the middle of our debates and our presentations. Alternatively, you can save them to the end, or we can just add them to the conversation at the end. Please feel free to join in the discussion and to give my guests a hard time if you feel that inclined. So what we're going to do now is we're going to pass over the baton to Paraskevas from NVIDIA. Well, I guess he will tell us the timeline maybe in a short moment. What was the transition from Mellanox to NVIDIA? Again, I'm not the expert. I'm going to leave it to the hands or in the hands of the person who knows better. So what is the need? What is the end goal for MASSTART? What should we see at the end of this project? Paraskevas, please.
So thanks a lot, Greg, for the introduction, and thanks also for inviting me to this great event. I will start with a few words about NVIDIA. I'm sure that the audience is probably very familiar with NVIDIA as the company that has invented the GPU and transformed computer graphics in our PC. Kevin, could you please go to the next slide? So NVIDIA, since then, NVIDIA was actually founded in 1993. Since then, it has evolved the GPU in a computer brain that is used, as we say, at the intersection of virtual reality, high-performance computing, and artificial intelligence. So very recently, in 2020, NVIDIA acquired Mellanox Technologies. Mellanox was a leader in high-performance interconnect technology, and this acquisition actually brought together two of the leading companies in high-performance computing. And it has also integrated a broad range of optical transceivers in the portfolio of NVIDIA. So in the next couple of minutes, I will try to answer this question that Craig posed. Why do we need MASSTART? What are the needs that led us to start this project, essentially? Next slide, please, Kevin. A few words about data center traffic. It's becoming a cliche to say that it's growing at an almost exponential rate, but this is the reality. There are a lot of studies. Most well known are the ones that have been conducted by Cisco, a lot of statistics showing this steep growth. We are experiencing a 26% year-over-year growth, and I think what is even more interesting is to notice that the vast majority of this traffic remains inside the data center. So it's more than 75% of this enormous traffic that stays inside the data center, and that requires a lot of high-speed interconnects. And of course, a lot of switches. So the figure on the left-hand side shows actually the forecast for the annual port capacity that is shipped on data center Ethernet switches, and it's shown in exabits per second. So we can see that there is. Yes, please.
I have a surprise question for you. Is that prediction still true? Looking at autonomous transport, for example, and the amount of data that these objects are expected to be producing, at least within themselves, and all these edge activities that I talked about today, data at the edge and manipulating data at the edge or manipulating it in the cloud. Are we going to see some sort of balance between where these operations take part, and within that, this prediction is still valued?
So this prediction is not a very old one. It's a quite recent one that was published by the IEEE last year. I think it was last April. It is taking into account all these trends, besides, of course, the very recent, let's say, COVID disruption. Right. It is taking into account all the machine learning, autonomous car trends, but of course there are a lot of assumptions that might delay or bring earlier some of these factors. So that could definitely change a little bit or shape this this graph here. Okay. Yeah, we shouldn't, of course, take this for granted, but we should just keep in mind that the trend goes on, so that the need for more traffic is there. And as you said, there are more and more reasons why we need more traffic, more and more applications why we need more traffic. In addition, let's say, to this very steep rise, because we are actually seeing this steep rise, we need a lot of transceivers. We need actually to upgrade the speed of our transceivers every few years. Currently, we are experiencing the ramp up of the 400 gigabit per second transceiver generation, and everyone is already working on the next generation, which is going to be 800 gig and then 1.6 terabit. And when I say everyone, I mean it's both industry, academia, and standardization bodies. It's the entire community. And then looking to the right-hand side, silicon photonics is becoming more and more relevant as the transceiver market is growing. And you can see on this figure on the right that the share of silicon photonics in the global transceiver market is expected to grow. The reason is that silicon photonics, as we all know, is based on the idea of leveraging the very vast infrastructure for silicon-based technology from the world of microelectronics in order to produce low-cost and large-volume photonic components. So as the transceivers are turning into a large multi-billion market, we are reaching the critical mass to benefit from the cost savings of silicon photonics. So if we can go to the next slide now, the big challenge is actually how we can bring these silicon photonic chips into transceivers and how we can package them. So packaging is actually a headache, packaging of the silicon photonic chips, because it contributes to the majority of the cost of the transceiver. Looking at this pie chart on the left-hand side, you can see that transceiver costs are dwarfed by the assembly and packaging costs, whereas the cost of the actual silicon chip is just a small fraction of it. And the reason is that because unlike electronics, photonics require very precise alignment with tight tolerances, and these are processes that are broadly done manually today. Historically, in every transceiver generation, we need to get a new reduction in the achievable cost per bit, as you can see on the graph on the right hand side. And now, as we are striving to go to $1 per gigabit per second and below, this existing approach simply cannot scale. So what we need is actually a disruptive path to further squeeze the cost. And this innovative path can be brought by automation. Next slide, please. Automation is the main theme in Massart, and of course we are applying this automation in transceivers, which we aspire to scale to the terabit scale. And to do that, we are considering a number of trends in the field, starting from the ramp up of 100 gigabit per second optics, and continuing also with the introduction of 100 gigabit per second electrical ports, as we see that 100 gigabit SerDes are becoming available. Regarding the speed evolution, there is a well-known paradigm that we can identify from the previous generations of transceivers. First, we see that the number of lanes is increased in order to increase the overall capacity of the transceiver using existing optics. And then once the higher speed optics are available, we move to higher speeds and consolidate the number of lanes.
So you mentioned in the last slide that assembly and test and packaging still remains roughly 70–80% of the pie chart in terms of total assembly. And that, I think, has been the case since a JEPIC research paper around about 2006. But I guess the justification for that still being applicable today is that these things are just becoming ever more complex and ever more multi-channel. So the assembly process consistently remains difficult. Yes,
this is overall true. Overall, the approach of using low-cost assembly in low-wage countries could scale up to a point, but cannot continue anymore. The complexity of the transceivers, of course, is increasing. The speeds are increasing. We also see that there is a notable shift from multi-mode to single-mode optics inside the data centers for various reasons, and that is really raising the bar in the assembly and in the tolerances that are required.
Thank you.
So, and actually, in order to answer or to add more to your previous question regarding the timeline for moving to different form factors, you can see this is a very simplistic graph, if you like, but it's actually aimed to show how we see the coexistence of different form factors over different generations. So as I said, we are now in 400 gigabit per second transceiver generations, and we expect that up to the 800 gigabit per second transceivers, we will continue to use pluggables for sure. That would be probably the point where we will see the first co-packaging products, and which will become more relevant and more popular in the 1.6 terabit transceiver generation. Next slide, please. So in this background, we can now devise a wish list for the next generation transceivers and see how these targets are addressed by Massart. First of all, we need high integration density. We need compatibility with high temperature operation, because in the data center we have high temperatures. We need high channel count and mass manufacturability. These are all aspects that can be enabled by silicon photonics, and in Massart we have the 300 millimeter silicon photonics platform of CEALET in France. On top of this, for these silicon chips, we need to have compatibility with advanced assembly techniques, and we are doing this by introducing through silicon via capability. We also need to have very low loss and high count optical IOs, and there are several lines, let's say, in the project towards this direction. We have in-plane and vertical couplers on the silicon photonics platform, and we also have dense fan outs on the WAFT platform of Team Photonics. And finally, we need to have a high TRL laser assembly, which is addressed by the silicon bench and assembly processes with appropriate alignment tolerances of dust photonics. So if we can quickly go to the next slide, to conclude, I would summarize the motivation of this project in just 3 short and simple messages. First of all, silicon photonics is becoming increasingly relevant for short-reach, low-cost transceivers. We really need to get dramatic reductions in assembly and packaging cost in order to meet our cost targets. And Massart is based on this motivation and is developing an end-to-end solution for mass manufacturable silicon photonic transceivers. So, and with this, I will hand over back to you, Greg.
Okay. Thank you, Paraskevas. How long has the project been running for already?
It's approximately 2 years.
And how much longer do you have to run? Just for the viewers' information. There's
for a year and a half.
Okay. On some of the slides we showed, I think there was the massstart.eu URL link, if anybody wants to find out more information and more detail, in particular about the people who are not here today as part of this presentation. But we haven't finished yet. We are going to go along to our Carla Flusky from ficonTEC R&D to give everybody here an outline of how ficonTEC is involved with this project and what our approaches are in solving the issues put forward by Paraskevas, for example. Carla, are you ready?
Yes, I'm ready. Thank you, Greg. So before I begin with the slides, just a quick hint. You can also find a lot of in-depth presentations of Massart project and a lot of the partners within the photonic that we presented in the Photonics Days in Berlin-Brandenburg last year. All the videos and the presentations are in the Massart website and can be accessed at any time. So this is just a quick hint for that. And then I would gladly start with the next slide, please, Kevin. Yes, so this is just a basic overview of all the steps of the way on a product value chain where you can find ficonTEC machines to accompany you along the way. So right after the device design, right on top, we can start R&D and prototyping with entry-level and standalone machines. And then we basically just accompany you along the way through validation and testing, process development, right into the production, testing, and up until the higher level automated machines regarding packaging and integration with the high volume inline manufacturing solutions that we have available. And this is exactly the point where we're going to tackle in Massart, and we are tackling that already. So then I will give you an overview of our ideas on the Massart in the next slide, please. Yeah, so here you have our basic ideas for the automated assembly line in Massart. So our main goal is to have a high throughput and low cost. So we are hearing what Paraskevas is saying to us. We are taking a look at that pie chart and seeing how much assembly has as a cost drive within the transceivers, and we are trying to explore alternative automation schemes to really raise the automation bar as far as possible and try also to make assembly lines as compact as possible. So within this idea, we are trying to condense 6 assembly steps into 2 machines to make sure we have a cost-effective solution, and also think about factory floor, how much footprint you're taking right over there. So for the first idea within this assembly line is to have 1 passive alignment machine and a second machine which performs the active alignment. So these are separated. We have 4 passive alignment steps and 2 active alignment steps. So these are also separated. And if you go for the next slide, please, Kevin. So there you have our concept for the first machine, which performs a passive assembly. So it consists basically of a robot that performs a pick and place and several assembly stations. This is scalable from 2 to 4. And these are the stations where the actual passive alignment takes place. So here we have also the possibility to be very flexible and also performing each station a single component as a passive assembly step, or we can also perform several passive alignment procedures within one assembly station. So both ideas are possible. And just to go a little bit more in depth in what one single assembly station can perform and our ideas for that, then you can move over to the next slide, please.
No, we can't. Can we go back? I have some questions, Carla, if I'm okay, if that's okay. So if I look at this, what I'm seeing here, I guess, is a division of labor in terms of what the robot arm does compared to what the different substations, let's call them substations, do within this system, right? One of the first things that occurs to me is that what happens, there's no redundancy for the robot arm.
We really considered that, and the good thing is that this is a tried and true industrial system, and this kind of robots, they are really already able to perform a lot of tasks. They are able to perform it very quickly, and these are industry standard nowadays for automation. So first of all, you have the low risk that it will really be such a liability, let's put it this way, that it's going to break down in a very unpredictable way. So the first one. And the second one is that we have in our machine so many possibilities of data analysis and to check at which point we should probably schedule already some downtime just to make sure that we have a proper maintenance, that we have that scheduled maintenances going on, and that we can really predict before a very critical part of the system breaks down.
Okay, so that ties in well with machine learning based topic we talked about in one of our previous webinars, I think, in terms of being able to predict anomalous behavior in certain components and then being able to, okay, so I understood. Let me throw in another question here. If Paraskevas was in a position to throw out a number for the number of transceivers he might need at 400 or 800G, then what you're saying is that robot is capable, more than capable, of dealing with that number of movements required to generate that number. What would that number be, Paraskevas, roughly?
So yeah, looking at the typical numbers and expectations, let's say in DR4 type transceivers, we are talking about 1 million transceivers maybe today, that would scale into a few million transceivers in the next 3 years, let's say.
Okay. And I think like millions of operations is standard behavior or standard performance for robot arms nowadays, right? So that question is answered, I guess. Thank you. No, there is a question I have here. That's something else I noted for myself. So what is the challenge for ficonTEC here? Let me. Kevin doesn't need to do this, but if we go back in our minds, go back a slide, you talked about automation, and I guess what you're doing here is you're looking at a lot of the ficonTEC systems are already highly automated. So it looks like here you're trying a different automation scheme in that you are generating or you're putting together substations within a single system. What is then the challenge for ficonTEC? What are we learning by this process, by this interaction within this project?
Yes, we are actually already very high in automation at ficonTEC. So here, of course, we're trying to make it very dense. So we are trying to raise up the level of operations so we can perform in a parallel way. Let's say 2 to 4 assembly stations working in parallel and trying to develop the process in the way that you can really perform the same activities within these separate assembly stations. This is one of the main, let's put it this way, challenges that we have.
So orchestrating the 4 substations together so that the whole process flows, right?
Exactly.
We have a question in the chat, Carla. So we have Nuno Edgar Fernandez in the chat. He has a question. So the robotic systems only perform pick and place?
For this case, yes. Within this scenario, we are trying to, maybe we can go for the next slide, and then I think this
maybe we can't, because there's another question.
Okay.
So he has two questions. The one is whether the robot arm is only performing pick and place, and the reason we should stay on this slide, I think, is the answer to his second question. The full assembly still requires manual input, question mark.
We are flexible in this way. Of course, we will need a feeding system if we wanted to do it in an automated way.
I mean, it looks like you have a conveyor system integrated into your
exactly
your CAD here, right? So, okay.
Exactly. So we have the possibility, of course, of a front loading from an operator. This is always possible, and it's there's of course nothing against that. But we can also include a feeding system that basically takes the parts already in trays and then just feed it into the system. So this can be done automatically with our standard state-of-the-art machines.
To answer Nuno's question more exactly, or to expand, this could be set up as a batch manufacturing system, right? With where it's feeding in from a cassette system, and also extracted. But you could also imagine an entire inline sequence of systems where components are brought in and the half completed module is passed on to the next steps, whatever they might be in a complete production line, right? And entirely, to be honest, this is probably how Parascavas would like to see this working as well.
Yeah, sure. This is not a problem also at all. So our machines are already in the field working in bigger lines. So this is completely within the realm.
Okay, thank you.
Okay, so if we go to the next slide, thank you. So this is just to show you a little bit of the new approaches we are working on for the small assembly stations. And when I say small and lower footprint, I'm talking about one station basically taking the space of a sheet of paper. And yeah, and we are also trying to reduce the autofocus time by roughly 50%. I'm pretty optimistical about that. I think we can even go higher by using all our software and hardware solutions that we're working on right now. And also to answer the question before, so here I stated also that we have this reduction in the motion time. And we are trying to separate basically the low motion range for alignment with the high precision. So we're going for the high precision where we need it, and going for a high motion range with a lower precision for pick and place, for having a wide range of motion in a very fast and high speed solution, and just focusing on the essence of what we need to perform within the small assembly stations. Of course, using the universal gripping technology to make these stations as flexible as possible regarding the part size, and also to be able to grip parts with different sizes, and also to the spatial optimization of the UV beam, just to make a more streamlined curing. So then we can go for the next slide. And then we move over to the active alignment machine. And this has a main goal of performing a very lean process. So we have minimal part handling before and after the alignment process, and we have a high flexibility to perform the 2 assembly steps in one machine subsequently. And this is basically what we're going for this alignment, for the active alignment machine. And then I would like to go over to the next slide, please. And just show you a couple of photos from the Massart setup that we have right now. So this is our basic proof of concept before we really make all assembly stations as tiny as possible and fill it in our machine. And we are ready to roll, and we cannot wait to start working the process development for the passive alignment machine. So,
thank you, Carla. Thank you indeed. And we have a question. I guess this question is really for everybody. Bogdan and Parascavas, yourselves as well. So we have a question from Maureen in the chat. And I think it's important that maybe everybody thinks about answering this together, or within the realm of what Massart has imagined for itself, what this needs to be. How fast is the assembly process for one, and I use the word carefully, prototype? And what is the minimum component size that can be picked up with this robot? I guess that second question then is for you, Carla. Would anybody like to lead with the first? Paraskevas?
Yep. So we have some internal targets here, but we should clarify that in the project we are using the automated assembly for the transmitter sub-assemblies, the transmitter and receiver sub-assemblies, but not for the entire optical cable, because we are actually building a pluggable optical cable as one of our prototypes in order to show the the real relevance, commercial relevance of the project. So we are taking the challenge all the way to the TOSA and ROSA, which is actually it's a real challenge, and we are not applying, we're not building a pilot line at this stage for the rest of the cable, which is much more straightforward in terms of equipment. So so we have targets only for the TOSA and ROSA. Maybe Carla is more more relevant to talk about that, because it's really implemented by ficonTEC.
So yeah, what we are trying to achieve right now is, as far as let's say cycle time goes for the, well, let's put it this way, for a TOSA, which is the larger component with more parts, so the bill of materials is considerably bigger, then I would say 2 minutes. So this is rough numbers, so please don't fix me on that, but this is just to have a sort of a feeling on which direction this is going.
And the minimum component size that can be picked up with this robot, or more exactly than maybe with the universal gripping tool?
Well, the universal gripping tool goes basically from everything that's above 500 microns up until several millimeters. So that's really a wide range. Okay. And basically the minimal size that we can pick with a robot depends a lot also on the tool that we apply to that. But I would say anything which is above 500 microns is good to go.
Okay.
Anything that's below that, then we need to maybe take a little bit more in detail look, but that doesn't mean it's not possible.
Okay. We have one more question from Mike Wong. Is the active alignment done using fast gradient search software algorithms and using 6 degrees of freedom?
Well, I would say I'm probably not the best person to specify that. I would really like to take this opportunity to say that we are only starting to work on the alignment processes, so we don't have anything developed right now. And we are developing also the strategies to work with the alignment. So I would say I would definitely have to get back to that.
Well, if we can, I think you're talking about your work within the project. I think Mike Wong's question can be more generally answered, and the answer to that questions in that case would be yes, of course, in both cases. We do have fast active search algorithms that we use in our standard systems that we sell, of course, and we have we can integrate any number of degrees of freedom. Very often systems go out with 2 sets of 6 degree of freedom motion systems built into them, so that you can do simultaneous dual fiber or fiber array alignment. So yes, on the one hand, within the project, that's not been defined yet. Generally, in terms of ficonTEC projects, absolutely not a problem. Any other questions, anybody in the chat? Not at this point in time. Kevin, if we can move to the next slide, please. We have an acknowledgement. Of course, we have to do that. This is an EU-funded program, funded project, funded within the framework program of the European Union, so the Horizon 20 framework program. It has a grant number. You can follow those links. If you note them down for yourselves, follow those links and find out more details. you will find out more details about what is actually going on currently and who the partners are within the MASSTART project by following the link that Suzanne Thoma shared with us in the chat. So that is massstart.eu. Of course, MASSTART is also an initiative put up by the Photonics Public-Private Partnership. So that's 4 Ps through photonics21.org. And at this point in time, we would like to thank both teams, both from IZM, Fraunhofer IZM, so Tolgan, Kai, Hermann, and Susan, and at NVIDIA, Boaz, I assume, Anna and Elad. Thank you for your contributions in helping Bogdan and Paraskevas, respectively, be able to provide details and qualified comments for this webinar. Kevin, if we can move on to the next slide. Thank you guys for the meantime. Please feel free to join or make any other comments if you feel you need to at this point in time. Quickly, for the people who have not maybe seen our webinars yet, who have not maybe seen previous versions of these webinars, we started these at the beginning of Q4 2020. We try to keep these short. We've gone over budget on our time this time, but we had a fair amount of ground to cover. Thank you for hanging in with us. We try to keep this short and bite-sized so that we are both flexible in terms of the content and our approach, and it means that everybody else and ourselves, we can all get back to work. What you will generally hear in these webinars, and this was a typical example today, some news and developments, in particular here, products, technologies, and in this case also projects that we are involved with other important partners. And we allow questions and answers both during the event, during the discussion, and afterwards, of course, by adding to the chat. The next webinars, these are scheduled for a Wednesday. They are not regular. Look on the website to find out when the next ones are coming. The next one, I believe, will be on April the 7th on wafer level testing. I mentioned this at the start of today's webinar. Depending on where you are in different parts of the world, that is your time of day. Be aware of the US that at the moment, summertime, wintertime for the US and for Europe is not synchronized, and that will remain unsynchronized until the end of March when Europe moves springs forward in the spring. Next slide, please, Kevin. If you want to find out more about, well, our partners in the discussion today, please follow the links to their websites. Fraunhofer IZM and of course NVIDIA are easily available and discoverable on the web, on LinkedIn and elsewhere. For ficonTEC, again, online, you can look at our homepage, look at some of the blog entries we have on our homepage. You can follow us on LinkedIn and Twitter. We have a Vimeo presentation where some of the videos we present are available. Again, you can look at previous webinars. And if you move to the next slide, please, Kevin. You can also try to reach us around the world. If you go to the locations page on our website, you will find detailed contact details for where we are available around the world. Please feel free to get in touch if you find you need to speak to somebody directly and have a direct conversation to solve your problem. I believe the next slide is the last slide. So, Bogdan, thank you.
Thank you, Greg.
Paraskevas, to you as well. Thank you very much for your time and your contributions. Carla, thank you for helping out with this further ficonTEC webinar. All your contributions are very helpful. I hope that was valuable to our audience. Again, thank you for your time. Thank you for hanging with us. And I guess we'll see you in April the 7th. Should be about 3 or 4 weeks' time. Look forward to speaking to you again with some interesting topics. Thank you, everybody, for your time. And goodbye. And thank you for the comments. Bye-bye.
Thank you. Bye-bye.
Thank you so much.
Bye-bye.
Bye. Thank you.